Okay, so we're going to finish off integration by parts in this section. That's going to involve me giving you a few extra tips for how you choose your U and your dVdx when you're doing integration by parts. So some advice on that. A couple of standard results, which you can see here on this first slide, and also introducing the idea of using limits. So for definite integrals, how do we do integration by parts? It's pretty similar, but just a couple of things we need to be aware of. So to start off with, I've got these four integrals here. Now I realize in hindsight that actually two of these are quite difficult, and I don't think it's really fair to ask you to just do them, but I am going to point out the two that you should be able to do. So you should be able to do the integral of tan x and the integral of cot x. That's within your knowledge. The integral of sec and cosec x are very tricky. They require you to use literally a trick, so a substitution, which it's not obvious at all that you would use it unless you already knew what the answer was. So instead, what I'm going to do is I'm just going to write the answer to those two. In the case of integral sec x, it's this. And in the case of integral cosec x, that's cosec by the way, CSC. That's just how the LaTeX software prints cosec. We get this answer. Okay. Now, in those two cases where I've given you the answer, you could go from right to left. So you could differentiate the right and end up with the left and satisfy yourself that it's true. So I might ask you to do that instead of the integral. So give it a go. Definitely try and find these two integrals here, tan and cot, see if you can get the answer. And as a bonus, see if you can also find the derivative of the right hand side of these two. See if you can get it back to sec and cosec. Give that a go. Pause the video now. Okay, so let's do integral of tan x first. So to do that, we're going to say this is the integral of sin x over tan, or over cos, sorry. And then we notice we're going to use the derivative of the bottom equals the top rule. So is the derivative of the bottom the same as the top? Almost. The derivative of cos x is minus sin x. So let's make it minus sin x and then put a minus out here. So now it will work. So it follows our rule. Derivative of bottom is the top, which means we can now replace it with ln of the bottom. Ln mod of the bottom. And the minus sign is on the outside. And then almost there, we're going to simplify this to ln of 1 over cosine x, right? Because the minus 1 can become a power, which is therefore then equal to ln of sec x. Okay, so that's it. We've got the integral of tan. The integral of cot is similar. You're just doing it a bit in reverse. So you've got cos over sine. And this time, the derivative of the bottom is exactly the top. So we don't even need to do the minus trick. And we can just say it's ln of the bottom. So we get ln of sine x plus c again. Cool. Okay, and if you did differentiate the right hand side, I won't do it here because I think it'll clutter up the slide, but you're effectively doing chain rule differentiation for both that one and that one. So you would get 1 over, in this case, 1 over sec x plus tan x multiplied by the derivative of sec x plus tan x. And that should end up getting you a bit of cancellation. You end up with sec x. So it's quite a complex looking answer, but it's all because everything cancels out when you work it out. That's part of the reason the substitution is difficult if you do it in reverse. Okay, so these four results are in the formula book, but it's useful to be, again, aware of them, know that they exist. you should definitely be able to derive these two yourself. And then the other two that I haven't circled, you want to be aware of roughly what they look like. Obviously, top students, feel free to memorize them. If you're not up to that, then you just make sure you're aware of what they roughly look like. Okay, so let's move on then with this topic of integration by parts. So I wanted to actually just, before telling you about my rules of thumb for which function you're going to do as u and which one you're going to do as dv dx within the rule, I wanted to show you a really cool little trick actually, which, I mean, it's not examinable in the sense that I would be surprised if such a tricky thing came up in the exam, but I don't think it's that hard to understand, and I think well, it's quite beautiful, so let me show it to you. It's this idea of recursion with integration by parts, and for a small number of functions you can do this trick. So let me show you that. What we're going to do is find the following integral. Okay, and it looks like quite a simple question, doesn't it? Just sine squared x. But it turns out it's not necessarily that obvious, and we're going to do a trick. So here's the trick. Let's first give this whole thing a name, okay, because we're going to need to use this later. Let's say that capital I, which is the integral we want to find, is the answer to that integral. Integral of sine squared x dx, whatever our answer is, let's call it capital I. Okay, and now we're going to use integration by parts, which means we need to turn it into a product. This comes into be a product quite naturally, right? It's sine x times sine x. Okay, so if we're going to use integration by parts, which one's u and which one's v dash, or dv dx, doesn't matter, because they're the same thing. So no confusion there. So you should be able to follow along with this quite nicely. U is sine x. I don't really need the implies there. Let's get rid of that. U equals sine x. V dash equals sine x. U dash, the derivative of sine x is cos. And for v, the integral of sine x is minus cos x. Okay, so what is this therefore equal to? Remember, it's going to be, let's write the full rule actually, it's going to be uv minus the integral of v u dash dx. So let's come down here to the bottom left and put that in. So u times v is minus sine x cos x. And then we're going to do minus the integral of v times u dash. That's minus cos x times cos x. So let's make that a plus here and just put in cos squared x dx. Okay, great. Okay, and now we're going to start doing some clever stuff. So we wanted to find the integral of sine squared, and now we've managed to turn it into some stuff here, plus the integral of cos squared. So it's like we've gone from one version of the problem, integrate sine squared, to another version of the problem, integrate cos squared, which is a bit annoying. But cos squared can be rewritten in terms of sine squared. So let's just try that out and see what happens. So this whole thing here is going to be, the stuff at the beginning stays the same, minus sine x cos x, plus, and I'm going to integrate cos squared x, but change it first. So now it's 1 minus sine squared, right? Because we know that cos squared is the same as 1 minus sine squared. So if I separate this out slightly, let's write it here, minus sine x cos x, it's actually the integral of 1 with respect to x minus the integral of sine squared x with respect to x. And then again, I'll write it here, minus sin x cos x plus the integral of 1 with respect to x is just x, and then this thing here, minus sine squared x, or minus the integral of sine squared x, Well, we said the integral of sine squared x has a name. We named it here, right? We said it was I. So let's replace that with the name for whatever we think that answer is. It's this unknown, capital I, right? So what have we just deduced here? We've deduced the following interesting property about this I. The capital I, our answer that we're looking for, is equal to minus sine x cos x plus x minus capital I. So can you kind of see what we can do here now? We can rearrange all of this, add I to both sides, and I'll get 2i, right? So I get 2i, that implies 2i is equal to minus sine x cos x plus x, or let's just rearrange it so that the minus sign is second rather than first. Then divide by 2, and I'm going to write the final answer in green. Capital I is therefore equal to the following. And that's it, that's the answer. We can throw in a plus c at the end as well. I really like this. This is very clever because it seems like we almost tricked, I don't know, it's almost like a trick, right? At no point does it feel like we've really done the integral, and yet we have derived a property which allows us to then find what the integral is. So that is the integral of sine squared x. It's x minus sine x cos x all over 2. And we've done this using integration by parts. This is not a technique that you're going to be expected to be examined on, I don't think, or examined on, I should say. But you know, hopefully you're not just here for the exam. So this is quite an interesting method, and in more advanced mathematics, you might see some sort of analogous techniques. But it's a good bit of practice. If you can follow this proof and you're happy with it, and that's a good sign that you're starting to see the appeal of this integration by parts method. Cool. All right. So let's look at now some more rules of thumb that we can actually apply for the easier case, or perhaps the less tricky case of integration by parts. Let's take a look at those. So there's this thing I found, which, I mean, I'm sure some other maths teachers use it as well. I never learned it myself, so I'm giving it to you more because it seems like it's a helpful rule of thumb, and it's been reported as a useful rule of thumb. What this rule is telling you is the order of priority of which function you should be labeling as your u. So if you remember, I'll just write it again. Our integration by parts formula. The question was always, or not always, but one of the questions was, which one am I labeling u and which one am I labeling v dash? So this LIATE rule, or LIAT, is suggesting that if there's a logarithmic function, make that your u. And if there isn't, if there's an inverse trig function, make that your u. And if there's an algebraic function, make that your u. If there's then a regular trig function, make that your u. And if there's an exponential function, make that your u. So usually exponential functions will not be your u because they're the last in the list, whereas a log function most likely will be the first thing you'll want to label as a u. So I guess let's just throw out an example. Let's say you had x squared times ln x. Then according to this rule, we're saying, well, this is algebraic and this one is logarithmic, so this should be our u. And this should be our v dash, right? Or if I had, I don't know, let's say sine x times sine inverse x. Oh, that's a terrible example. Hang on. That'd just be the number 1, wouldn't it? Cos inverse x. Oh, I shouldn't write. I don't like -1. Let's call it arc cos. But you get the idea, hopefully. So that in this case is an inverse trig function higher in the priority list, so make that your u and make that your v dash. Okay, so that's the rule of thumb. Please don't treat it as, you know, gospel. It's not 100%. It may not always be the case you follow this rule, but this is generally a good guide. If you're completely stuck, then try this first. And worst case scenario, you might get a dead end, in which case you just do it the other way around. But more often than not, this priority list should work for you. So just keep that one in mind. Okay, and then the last thing I want to talk about, for which I'll then give an example, is the version of integration by parts with limits. And it's quite logical. It's basically the same formula, just with a few bits of extra syntax added. So we said integration of u v dash equals uv minus integral of v u dash, and let's put the dx's in. That's the rule. With the limits, so let's place limits here. Let's be generic and call them a and b. If you've got limits, then all you're going to do is add limits here, and then this part, uv, that's just a function, and it's like an integrated function. You just put square brackets around and you apply the limits that way. So this part here is effectively what you do after you've integrated, right? It's uv, put in b as your value, and then take away uv of a, right? Because you've got integral equals function minus integral. When you add limits, it becomes some constant equals a constant minus another constant. So we're equating the same types of mathematical objects. Okay, so that's it. That's the integration by parts with limits on it. Really, that's the full rule. But we just saw the simpler version first, just so we could get used to it. So let's look at one example of how to use this, and then I'll give you some questions. Okay, we're going to evaluate one or LUNX from 1 to 2, leaving your answer in terms of natural logs. Okay. Right, this example doubles as an example for how to use the limits, but also an example of another slight trick. Well, using that Layat rule, I guess you might suspect that LUNX, we're going to label that as u. But this doesn't seem like a product, right? There's just one function there. So what's going to be our v dash? In this case, this might be a legitimate technique to use sometimes, quite rarely, but in this instance we can use it. We're going to just multiply by 1, and we're going to say that 1, that's our v dash, right? I haven't changed the integrand, right, the thing within the integral. It's still LUNX. I've just stuck a 1 multiplier on the outside, so that I can now artificially create a product, which is going to be u and v dash. So let's note that down then. We've got u as LUNX, we've got v dash as 1. LUNX differentiated becomes 1 over x, and v dash integrated back upwards goes to x. So therefore this is equal to uv, which is x LUNX, and now let's put the limits in from 1 to 2, minus the integral of v u dash, so that's x times 1 over x dx, and conveniently x times 1 over x just becomes 1. So then this whole integral becomes 2 times ln 2 minus 1 times ln 1, which is just ln 1, and then minus, I didn't put the limits in, silly me, that's the whole point. What is the integral of 1 from 1 to 2? We can do that as an aside. It's almost so simple it's confusing. The integral from 1 to 2 of 1 with respect to x is equal to x taken from 1 to 2, which is just the number 1. So it's just minus 1. And then that gives us 2 ln 2 minus, what's ln of 1? Well, e to the power of 0 is 1, so that's 0 minus 1. 2 ln 2, I'm just going to turn that into ln 4. 2 squared minus 1. And that's it. We've got the answer. Ln 4 minus 1. So final bit of practice then for now of integration by parts, this time using limits. 2 slides, 2 questions on this slide and 1 on the next. This first set just to practice a bit more using integration by parts. What I'd suggest is maybe try using that Lyot rule, see if it works out for you. I haven't tried using it myself, but see how it goes, and if you feel like it generally works, then that's quite a good sign for you to stick with it. Any exceptions to that rule, feel free to let me know actually, and we can take a look and see why it's failed. Then try number 6 as well. See if you can find the answer to that one. You can pause the video now. Okay, and then a final question for you to try, proper exam style question. Can we find the integral of sec squared? And xx squared as well. Yeah, give that a go. You can pause the video now.